Good morning, students. Myself, Dr. S. Devikala, Associate Professor in the Department of Chemistry, SRM Institute of Science and Technology. In today's class, let us discuss about thermodynamics. The word thermo means heat, dynamics means flow. So, thermodynamics means flow of heat. It deals with heat and energy changes, how heat and energy exchange with each other. Let us see one by one. So, what is thermodynamics? So, it is a branch of science which deals with energy interaction and its effect on the system and surroundings. So, thermodynamics can be defined as the study of energy, that is, energy transformation and its relation to matter. The analysis of thermal system is achieved through the application of conservation equations, namely conservation of mass and conservation of energy. As we know, in thermodynamics, we'll be using more often, we'll be using these two terms, system and surroundings. So a portion of matter that is under investigation is termed as system. All the other portion, whatever it is remaining except the system, the remaining is called as surroundings. There will be a real or imaginary line between the system and surrounding that is called as boundary. A system can be defined like this. A thermodynamic system is that portion of the universe that we have selected for investigation, whereas surroundings, everything, that is the mass or region outside the system, except system, whatever that is remaining, that is generally called as surroundings. Then the third term, boundary, the real or imaginary surface that separates the system from its surroundings is called boundary. So chemical system generally classified into three types: open system, closed system, isolated system. In case of open system, both heat and matter can exchange, whereas in closed system, only heat exchange, there is no matter exchange. In isolated, neither heat nor matter can be exchanged. So let us see one by one. In open system, mass and energy can be transferred through the boundary, whereas in closed system, energy exchange with the surrounding but no mass transfer, whereas isolated system incapable of exchanging both energy and matter. For example, open system, a glass containing water, that is open; closed system, water bottle containing water, whereas the third one, isolated system, a thermoflask. There are two types of properties, namely extensive and intensive. Intensive properties are those which is independent of quantity of matter, whereas extensive properties which depends on the amount of matter. Some of the examples of extensive properties: temperature, pressure, density, whereas extensive property, mass, volume and total energy. Let us see what are all the processes or cycles involved in order to attain or in order to convert a reactant A to B. From A to B, there are two ways. Either through this path we can attain B, or the other path is mentioned here. To specify a process, initial and final states and the path must be specified. Processes are of two types: reversible process and irreversible. In case of reversible process, the system changes back to the initial condition along the same path. The magnitude of change of thermodynamic quantities in the different stage will be the same in the forward and backward reaction, but with opposite sign. Such type of process is known as reversible, whereas in case of irreversible process which occurs suddenly or spontaneously without the restriction of the occurring in successive stage of infinitesimal quantities. Let us see about the different types of chemical reaction: exothermic reaction and endothermic. Exothermic is one where heat is liberated. Endothermic is one, heat is absorbed. Based on the condition, several processes are there: isochoric, where there is no change in volume; isobaric, there is no change in pressure; whereas isothermal, pressure remains constant. In adiabatic, no heat leaves or enters the system. So isochoric process, delta V is 0, that is no change in volume, temperature and pressure will increase. Whereas in case of isobaric, delta P is equal to 0, no change in pressure, temperature and volume will increase. Whereas in isothermal, no change in internal energy and also no change in temperature. In adiabatic, delta Q is 0, no heat leaves or enters the system, temperature of the system changes. Let us see the zeroth law of thermodynamics. If two bodies are in thermal equilibrium with a third body separately, they are also in thermal equilibrium with each other. So in this, 1 represent A and C are in equilibrium, 2 represent B and C are in equilibrium, whereas 3 represent A and B are also in thermal equilibrium with each other. Several thermodynamic terms are there. Let us see one by one. First one, internal energy. Internal energy of the system, it is nothing but energy content of the system. It is denoted by capital E or U. The absolute value of E cannot be determined, only the difference. That is difference, it is represented by delta. So delta U or delta E alone calculated. It is one of the extensive property and it is also a state function. Extensive property is one that depends on quantity of matter. Depends on the amount of mass. So a measure of delta U is measuring heat release or taken up at constant volume. Let us see the first law of thermodynamics. Everybody known, this is well known to everyone. Energy can neither be created nor be destroyed, but it can be transformed from one form to another. It is given by the simple equation, thermodynamic expression, Q is equal to delta U plus W, where Q quantity of heat, W amount of work done. Whereas delta U change in internal energy. Either it can be represented delta U or delta E also. Enthalpy is nothing but heat content of the system. It is denoted by capital H. It is given by the expression, mathematical expression, H is equal to U plus PV. So if you calculate the difference in enthalpy and internal energy, pressure remains constant. So the equation becomes dH is equal to du plus pdv plus pdp. So change in enthalpy is nothing but heat of the process of constant pressure. So enthalpy, it is also an extensive property. It is also a state function. This slide we can skip. Let us see about the spontaneous processes. Spontaneous processes are those that can proceed without any outside intervention. The flow of water from the waterfall, that is the well-known example for spontaneous process. Then the third term will be entropy. Entropy, it is nothing but it is the measure of randomness, or it is a measure of disorder of the system, where S is equal to dq reversible by T, where T is absolute temperature, S represents entropy. Molecular disorder or molecular randomness, that is known as entropy. So entropy, we can relate entropy with the spontaneity of the process. So S universe is equal to delta S system plus delta S surrounding is equal to 0. Entropy change in reversible process for universe is 0. For an irreversible process, it is greater than 0. Irreversible process is also known as spontaneous one. So the next term will be free energy. Free energy, it is also known as Gibbs free energy. Then the second term is Helmholtz free energy. Gibbs free energy is given by the relation G is equal to H minus Ts, where G is free energy, H enthalpy, T absolute temperature, this is entropy. Let us see the Gibbs-Helmholtz equation derivation. So here, as we know, the Gibbs equation, G is equal to H minus Ts, H is equal to U plus PV. Therefore, if you combine these two, G is equal to U plus PV minus Ts. So if you differentiate, dG is equal to du plus P delta V plus VdP minus TdS minus SdT. Let it be equation number 4. From the first law of thermodynamics, we know that du is equal to dq minus P delta V, and applying dq is equal to Ts, the equation becomes du is equal to TdS minus TdV. By replacing the value of du in equation 4, in this equation, we'll get the above expression. If you simplify further, you will get dg is equal to vdp minus sdt. When the pressure remains constant, the equation becomes dou delta G by dou T at constant pressure. Since it is constant, we have to enclose outside the bracket, which is equal to minus delta S. That is difference in entropy. So if you simplify further, we know that delta G is equal to delta H minus T delta S from equation 1. So if you equate left hand side and right hand side, the equation becomes final equation delta G is equal to delta H plus T into dou delta G by dou T at constant pressure. This equation only it is known as Gibbs-Helmholtz equation. So here delta G is nothing but rate of change of free energy with the temperature at constant pressure, that is temperature coefficient of free energy change. Let us see the applications of Gibbs-Helmholtz equation. It is used to calculate delta H of any reaction from delta G and its variation with the temperature at constant pressure. This application is useful particularly in relation to reversible reactions in case of electrochemical cells. In forthcoming classes, we will be seeing what is electrochemical cells also, where delta G identifies with the electrical work done, that is minus NFE, N number of electrons transferred, F Faraday, E EMF of the cell. And then the second application, it will be calculate delta G of any reaction at a temperature other than 298 Kelvin. And then the third application, calculate the effect of temperature change on the equilibrium constant, that is Kp. Then we can relate standard free energy change in chemical reaction with the help of this equation. Delta G naught is equal to delta H naught minus T delta S. So there is no way to measure absolute enthalpy, although we can measure changes in enthalpy only. This point I told you already. Internal energy, enthalpy, entropy. For everything, the absolute measurement, the exact value is not known. Only we can find the difference in enthalpy, difference in internal energy, and difference in entropy alone can be calculated. So because enthalpy is one of the component of Gibbs free energy, we are unable to measure absolute free energies. We can measure only the changes in free energy. The standard free energy change, that is delta G naught. Whenever this naught is there, no, then we have to call it a standard state. It is a change in free energy when one substance or a set of substance in the standard state is converted to one or more other substances also in the standard state. The standard free energy change can be calculated from the definition of free energy if the standard enthalpy and entropy changes are known. Free energy and equilibrium constant. For spontaneous reaction, that is for irreversible processes, delta G decreases. It becomes less negative as the reaction proceeds towards equilibrium. At equilibrium, delta G is equal to 0. Therefore, delta G is equal to delta G naught plus RT ln K is equal to 0. Where what is delta G naught means standard change of Gibbs free energy. Then delta G naught is equal to minus RT ln K, or ln K is equal to minus delta G naught by RT. Here delta G naught is said to be calculated at temperature T. K is known as equilibrium constant. When delta G naught is less than 0, whereas K greater than 1, the reaction is favored towards the product. Whereas delta G naught is greater than 0, K is less than 1, then the reaction is favored towards reactant. When delta 0 is equal to 0, K is equal to 1, the reaction favors neither reactant nor product. The temperature dependence of free energy comes from the entropy term. By knowing the sign, whether it is plus or negative, positive or negative, of delta S and delta H, we can get the sign of delta G and determine if a reaction is spontaneous or not. So this table, this tablet column, you all must remember. If you remember this, it will be easy to predict whether the reaction is spontaneous or non-spontaneous. Okay. So if delta H is plus, delta G plus, minus T delta also plus, delta S alone minus means then the reaction is non-spontaneous. Likewise, spontaneous, low temperature spontaneous, high temperature non-spontaneous, low temperature non-spontaneous, high temperature spontaneous. So I hope you have understood today's class. We have explained, we have seen what are all the terms that are used in thermodynamics. Apart from that, we derived the Gibbs-Helmholtz equation, and we have seen some of the applications of Gibbs-Helmholtz equation also. Thank you.